Welcome to Basics of Finite Element Analysis Part 2. This is the fourth week of this ongoing course, and what we will do today is continue the discussion which we were having last week, that is how do we go around solving a two-dimensional problem with one variable, and specifically in the last week we had started discussing the Poisson's equation. So, we will continue to do that discussion, and hopefully by end of this week we would have formulated the problem using the finite element method and also developed interpolation functions for the same. To recap, the model equation was something like this. So, it is partial derivative with respect to x, a11 del u del x plus a12 del u del y minus partial derivative with respect to y of a21 del u del x plus a22 del u del y plus a00 times u minus f equals 0. And we had said that if a11 is equal to a22 and a12 equals a21 equals 0, and if a00 was also 0, then we can express this equation in the following form. So, a11 equals a22 in this case, if it is equal to some number a or function a, then I can express this as equals f, or I can express the same equation in vector notation. So, this is my operator, divergence operator times a times gradient of u equals f. So, these forms this form or this form is known as Poisson's equation. Okay. And to recapitulate, this operator is nothing but a unit vector times del over del x plus another unit vector in the y direction times del over del y. Now, this operator, this definition is valid for Cartesian frame. Is valid for Cartesian frame of reference. For cylindrical frame, spherical frames, this definition changes, but we can still, but for other frames this equation is still valid, but it is just that the operator's definition changes. So, what we had said was that the way to solve this Poisson's equation, or for that sake even this equation, would be pretty much similar to the way we had solved one dimensional problems, which we had discussed in part 1 of this course. So, the approach would be to solve so this is equation 1. If I have to solve this equation 1, then approach would be, first we have to discretize the domain Then we have to develop a weak form of this equation which is applicable to a element of the system, not to the whole thing, but for element, because that is where finite element comes in. So, weak form for individual element then we put in the weak form. So, in the weak form what do we do? Approximation functions for UE. So, we develop the weak form and then in that weak form we put in approximation functions. So, then at this stage we get element level equations. And then the next step is that we perform assembly of equations. Once we have done the assembly, we apply boundary conditions and then we solve the problem. Solve the equations for unknown variables. And later if we want, we can do post processing of that result. We do post processing of the result. So, all these steps at a conceptual level they are same as what we had encountered when we were doing FEA part 1, which was in the last semester. So, all those these steps are same, but what differs when we move to two-dimensional problems is significant difference in developing the weak form, because here when we do integration by parts, we are talking about a two-dimensional domain. In earlier system it was one-dimensional domain. So, the results yield some different type of terms. Then the other important difference lies in developing the approximation functions, and they are also significantly different than what we had seen in one-dimensional things. And then also the assembly of the equations. So, these three things are significantly different in two-dimensional, and if we learn how to do it in two-dimensional space, then it is easy to graduate to three-dimensional systems, because there the concept is essentially still remains the same. So, with that intent we will solve, or we will develop a finite element formulation to solve this equation 1 or its simplified version, which is the Poisson's equation. And the first step which we had said was we discretize the domain. Discretize the domain. So, this is again we are recapping. I had explained this earlier. So, if this is my domain where I want to find the solution, let us say I want to break it up into triangles. So, this is my discretized domain, but the important thing to note is that these areas of red, when we discretize it, they do not get captured in the domain. So, this is something very fundamentally different than what we had seen in one dimensional problems, because there it was a straight line element. So, I could break it up into smaller line elements and the entire length of the line would be covered. Here the entire surface area is not covered, especially if the outside parameter is a little complicated. So, this introduces what I had said was domain approximation error. Or discretization error. So, this is one additional error which comes into the picture when we handle 2-dimensional or 3-dimensional problems. So, this is what I wanted to recap in context of whatever we had done earlier. Now, what we will do is we will start developing a weak formulation of the problem. So, we have talked about this discretize the domain. The next step is weak formulation of the problem. So, we will write down the equation once again. The equation is minus del over del x A11, and what I will do is just to make things in brief, sometimes I will also write del u over del x as ux and del u over del y as uy. So, this is ux plus A12 uy minus del over del y A21 ux plus A22 uy plus A00 u minus f equals 0. Now, I can call this entire expression as f1 and I can call this entire expression as f2. So, one minus del over del y f2 plus A00 u minus f equals 0. Now, we are interested in developing its weak formulation. So, what do? We find out, so if my solution for u is accurate, then the left hand side will equal exactly 0, right, at all points, at every individual point in the domain, at every location x y coordinate, the value of left hand side of the equation will be exactly 0, which will equal the right hand side. So, in that case my solution will be exact and there will be no error in the solution. Now, when we are talking about approximate solutions such as finite element analysis, this error is not going to be 0. So, for approximate solutions, left hand side is not necessarily equal to 0, and that introduces an error in the system, in the equation. And this error, so let us call this error as E. This is a function of x and y. It changes from point to point. So, it changes from one point to other point. So, when we are doing finite element analysis, we say okay, we realize that there is a point to point error in the system, but what we want is that if I multiply this error with a weight function w, and this weight function is also a function of x and y. So, if I multiply this error with a weight function and then I integrate it over each element, okay, and we want to develop a solution that, okay, its error may not be 0 on a point to point basis, but the multiple of the error and the weight function when I integrate it over the area of the element, that should be equal to 0. So, this is the weighted over element is 0. So, the error is not 0 at every specific point, but the weighted residue over the entire element, it is 0. So, kind of in a sense, and the error is 0 in an integral sense over the entire element. So, this is, so let us call this equation A and we will call this equation B. So, now what I do is I plug in this equation in equation B to get. So, before I do that I wanted to make you understand or explain it clearly that in one dimensional system we were integrating it over the length of a element which was a straight line. Here the element could be a triangle, it could be a rectangle. So, we are integrating it over the area of the element. So, that is why we have two terms dx and dy, and also this omega e represents domain of the element. Where E stands for element. So, for each element omega is the domain. So, omega E, omega superscript E represents domain of the eth element. So, this equation is specific to an element, this is important to understand. For another element it will be a different equation. So, this is an element specific equation, this is important to understand. So, the next thing we do is we plug in this equation in equation B. So, what we get is integral over the domain of the element w times minus del over del x f1 minus del over del y f2 plus a00 u minus f dx dy equals 0. So, next what we do is we weaken its differentiability. We weaken the differentiability of the system. So, before we start doing that, I wanted to explain that the term f1 has first order derivatives of u in x and y. Same thing is true for term f2, it is having ux and ui. So, it is having first order derivatives of ux of u in x and y, and f1 is being differentiated with respect to x and f2 is being differentiated with respect to y. So, in this weighted residue statement, which is this equation, I can call this B1. In equation B1, we suppose we replace u with some approximate function of x and y, then it should have at least what order of derivatives? It should have second order derivatives, right? It should have at least second order derivatives, because if the order of derivatives is if it is only differentiable once, then all the term these related to f1 and f2 will become 0. So, it should have second order derivatives. So, in that context we will start developing an approach where we will develop a weak form of equation B1, and in that case the differentiability requirement on u, which right now as per equation B1 is 2, it will go down to 1. So, that is what we will do in the next class. So, we will continue this discussion in the next class, and we look forward to seeing you tomorrow. Thank you.